So when preparing a buffer, there are two things that you need to pay close attention to. One is the working pH range of the buffer, and the other is the capacity of the buffer. And these two things are um, basically independent of each other. They're related by the identity of the acid and base that you're working with. But it's important that you not confuse these. So these two things dictate how much acid and base can be neutralized before a pH change will occur. And it also, so that's the capacity, how much acid or base can be added. The working range is around what pH. So when you're preparing a buffer, you need to choose an appropriate conjugate acid-base pair. And a buffer, this is a good definition. A buffer has a working range of plus or minus 1 pH unit around the pKa of the acid. So I've jumped to a table here that has pKa values shown. I said a buffer has a working range of plus or minus 1 pH unit around the pKa. And this table is common acid bases used for a technique called high performance liquid chromatography. You don't need to know that. There are lots of different reasons people use buffers. In HPLC, buffers are important. But here acetic acid is shown. And the pKa for acetic acid is given as 4.76. I think that's a little different than what we're given in our lab today, but don't get hung up on that. So our buffer could be anywhere from 3.76 to 5.76, with it centered around 4.76. So 5.76, 3.76. So that's our working range. And I'll when I have a slide with a little more white space, I'll expand on why that is. I'll give another explanation of why that is. So that's the working range. So if you need a buffer at pH 4, you want to hold the pH at 4.00, you could use acetate and acetic acid, and then we're using sodium acetate in this example. There's also potassium acetate. It doesn't really matter what the counter ion is. It's a spectator. We're interested in just the acetate. But we couldn't use phosphoric acid or sodium phosphate because the Ka's, phosphoric acid is a triprotic acid. It has 3 protons here. You may have to look closely to see the subscript 3. But there are at 2.15, 7.2, and 12.15. If you've ever power washed your house, you may have used TSP, trisodium phosphate. It's very alkaline. That's what TSP is. You can go to the hardware store and pick it up. It's a white powder. It's the trisodium salt of phosphoric acid. But you would never use phosphate to make a pH 4 buffer because the pKa's are not appropriate. So the working range is not appropriate. So you can find different acid-base pairs that will give you pHs over a range, but you need to choose the right one to make your buffer. So that was talking about the working range of the buffer. Now, I promised you I would explain something in a little more detail. In the Henderson-Hasselbalch equation, we have pH equals pKa plus the log of the conjugate base concentration, or the anion, over the concentration of the acid, and I'm just using these generic placeholders, HA and A. At the pKa, when the pH is equal to the pKa, this term is 0. And when is this term 0? Well, this term is 0 when HA concentration equals the conjugate base concentration, and then that ratio is 1. And the log of 1 equals 0. Now, if we have if this term is equal to 10, or this term is equal to 0.1, then the pH will be 1 unit away from the pKa. You can get your calculator out and convince yourself that that's true. So that's what determines the working range of the buffer, when we can have 10 times as much conjugate base, or we can have 10 times less conjugate base, and the buffer will still hold. But if we move beyond 10 times above or 10 times below, then the buffer doesn't hold any longer. So that's where the working range of a buffer comes from. It's related to this ratio. Now, the second part, so we've just focused on working range. The second part is the capacity. How much acid or base can be neutralized before the pH changes? And this is related to the concentration of the buffer. Okay. Now, if you know about how much of an insult, how much of a change you're going to be subjecting your buffer to, the amount of added protons or the amount of added hydroxide, you calculate that, and then you make sure that the concentration that your buffer has is equal to or greater than that concentration. Now, you might be asking, well, why don't I just use the highest concentration possible, and then I don't have to worry about how much my buffer is going to, how much acid or base my buffer is going to encounter? And to a first approximation, that's not a bad idea. The problem, particularly in biological systems, is that the osmolality of the solution is related to the concentration of all the species in solution. And if I have a very high buffer concentration and I put a cell in that buffer, due to the hypertonic concentration of the buffer, the cell will lose water and it'll shrink. So I can't ignore concentration because it has impacts on other aspects of the experiments I'm conducting. So I don't want to just maximize concentration, because that will probably not be acceptable for other aspects. That's why I have the word appropriate, because it's got to be appropriate for the situation you're working in.